Hello and welcome. Today we are jumping right into the very foundation of physics. Before we can talk about big ideas like how planets orbit or what happens inside an atom, we have to get a handle on the basics, how we actually measure the world around us. So let's get into it. You might think physics is something that only happens in a laboratory, but nope, it's literally everywhere. I bet you've seen a sign just like this one, right? On an overhead bridge, maybe. It seems like a simple warning, but for us, this is where our physics journey begins. So let's take a closer look. What is this sign actually saying? I mean, it's not just some random number and a letter thrown together. It's a really precise piece of information with a super important real-world consequence, especially if you're driving a tall truck. And this sign is a perfect example of what we call a physical quantity. That's just a fancy term for anything that you can measure. The most important thing to get is that it always has two parts. First, the number, the magnitude. That's the 4.5. And second, the unit, the M for meters. You absolutely need both. 4.5 means nothing without the meters part. This idea brings us to something huge. You can think of measurement as a kind of language. And for science to actually work, everyone, no matter where they are in the world, has to be speaking the same one. Just imagine for a second, what if people use their own body parts to measure stuff? Like an engineer in one country measures a car part using their own foot, and an engineer somewhere else uses their hand. It would be total chaos, right? Well, this was a real problem way back when. It created so much confusion because nothing was standardized. So what was the solution? This right here, the International System of Units, or as everyone calls it, SI units. You can think of this as the official, global language for all of science and engineering. It means that a meter in Japan is the exact same length as a meter in Brazil. It's universal. Now, what's really amazing is that almost any measurement you can think of, speed, pressure, energy, you name it, can be built from just these 7 base units you see on the screen. For O-level physics, we're going to be laser focused on the top 3, the meter for length, the kilogram for mass, and the second for time. They are the absolute bedrock of everything. So physics deals with some seriously extreme scales, from things that are ridiculously big to things that are unbelievably small. And writing out all those zeros every single time, yeah, that would be a total nightmare. So naturally, we came up with a better way. Just look at this number. This is about how far apart air molecules are. I mean, come on, trying to write that or even say it out loud is just clumsy. And it's so easy to accidentally add or miss a zero and throw your whole calculation off. So you've got to be thinking, right? There has to be a better way. And you'd be right. Scientists, being the efficient people they are, developed a brilliant shorthand for exactly this problem. And here is the solution: prefixes. Each of these little prefixes is basically a code for a power of 10. So instead of writing out 9 zeros for a billion, you can just use giga. Or for that super tiny number we just saw, you can use nano. It just cleans everything up and makes life so much easier. Okay, check this out for a real-world example. Scientists actually built a guitar that's only 13 micrometers long. You see that little mu symbol? That's the prefix micro, and it means 1 millionth. Isn't writing 13 mu m just so much cooler and easier than writing 0.000013 meters? For sure. All right, so now we know the language of measurement. Let's talk about the tools, because getting a good, accurate measurement isn't just about being careful, it's about picking the right tool for the job. First up, the good old meter rule, your classic ruler. This is perfect for everyday stuff. The length of your desk, the width of a book. It's your trusty go-to when you don't need insane levels of precision. But what if you need to measure something smaller and you need to be more exact, like the thickness of your phone, maybe? That's when you level up to digital calipers. They'll give you a way more precise reading for these smaller kinds of objects. And for the really, really tiny things, well, then you bring out the champion, the micrometer screw gauge. This is the tool you'd use if you wanted to measure the thickness of a single sheet of paper or even a strand of hair. It's the king of precision for the small stuff. So here's the bottom line all laid out for you. Just look at the smallest division each tool can handle. A meter rule gets you down to a single millimeter. The calipers are 10 times more precise than that. And the micrometer, it's 100 times more precise than the ruler. The lesson is simple. Choose the tool that fits the precision you need.
Now listen up, because even with the perfect tool, you can still mess things up. One of the most common mistakes is something called parallax error. If you look at the measurement from an angle, like you see on the left, you're gonna get it wrong. You have to look at it straight on with your eye directly above the mark, just like on the right. That's how you get a true reading. Okay, we're on to our final big idea for today, and it's a game changer. Sometimes just knowing how much of something there is, well, it isn't the full picture. Sometimes you also need to know which way. And this brings us to the difference between a scalar and a vector. It's pretty simple, actually. A scalar is just a number, a magnitude, like saying 5 meters. But a vector has both a magnitude and a direction. So you'd say 5 meters to the east. It seems like a tiny change, just adding a direction, but trust me, in physics, this changes absolutely everything. This little diagram of a trip from point A to point B shows it perfectly. See that winding green path? The total length you actually walked, that's the distance. It's a scalar. But that straight red arrow from your starting point to your ending point, that's your displacement. It's a vector, because it has a length and a very specific direction. And here's why that matters in the real world. Let's say this athlete runs 200 meters along the curve of the track. That's her distance. But look, her displacement, the straight line from start to finish, is only 50 meters, pointed south. This is super important because speed is based on distance, but velocity is based on displacement. Two totally different calculations. So let's wrap this up with a final question to get your brain working. If you run one full 400-meter lap on a track and you end up exactly where you started, you've run a distance of 400 meters, for sure. But what is your displacement? Think about it. The answer is 0, a big fat 0, because your final position is the same as your starting position, so you haven't been displaced at all. And that's the cool and sometimes tricky power of vectors. Thanks for joining me.